So, a set of notes for you, equilibrium and thermodynamic wrap-ups. There's a set of notes in Schoology for this. It may be called Kinetics and Thermodynamics, Final Thoughts, or something along those lines. The notes are there. You may use those, or you take your own. You know the drill. All right, so we've had this graphic up throughout the entire unit, reminding us that thermodynamics tells us about the beginnings and the ends of a reaction. Kinetics tells us about what happens in between. Okay, so when we think about this, a common question that chemists will ask is which is controlling or which is dominating how the reaction proceeds? Is it the thermodynamics or the kinetics? In other words, if a reaction happens, is it happening because of kinetics or thermodynamics or both? Okay, so to think about this idea, kinetic versus thermodynamic control, we're going to consider two reactions, blue and green, with the same reactant. Okay, so if you think about it here, which reaction is favored thermodynamically, which reaction is favored kinetically? Take a moment, think about it, come up with some ideas, and then we'll talk about it some more. So to be favored thermodynamically, in thermodynamics, we're talking about delta G, delta H, delta S, okay? And in terms of kinetics, we're talking about rates and mechanisms, right? All right, so which reaction is favored thermodynamically? In other words, which one is going to happen, more likely happen based on the beginnings and the ends? Well, beginning, end. And we'll see that P2, the blue one, has a greater delta H in magnitude than P1 does. So we would say P2 is thermodynamically favored. Which one is favored kinetically? Well, kinetics deals with what's going on in between. And we can see here that our activation energy for the green TS1 reaction is actually less than that of EA2, okay, which has a higher activation energy. So which reaction is going to happen faster? EA1, or sorry, TS1, okay? So which one is more likely to be, or more favored thermodynamically? TS2. Which one's going to happen faster? TS1. This leads to a whole bunch of different conclusions that we can make about these. So blue is favored thermodynamically. Delta G is more negative, delta H is more negative. We have the more stable product, right? Lower energy is P2. So that means P2 is what we call the thermodynamic product. It's the one that's favored thermodynamically. Green, again, is favored kinetically. It is got the lower activation energy, which means it's a faster reaction. So it is the kinetic product, okay? So which reaction actually happens then? Well, this depends upon conditions. Think about what might cause one thing to be favored over another. When is the conditions what controls whether something is thermodynamic or kinetic. So hopefully you honed in on temperature, and you can think about this one. So at a low temperature, okay, so molecules are moving but not super fast. So which hump can they get over? It's more likely they're going to get over activation energy 1, but they're not going to be able to get back. So P1 forms, the reaction goes to completion. Molecules cannot get over EA2, so this one would be kinetically controlled. So at a low temperature, this reaction would form product number 1. Okay? If we were at a high temperature, though, the particles can do a couple things. One, they can likely get over the higher hump, and it's likely that if the temperature is high enough, they might be able to get back as well. So that means that we could have the possibility of P2 forming in some kind of equilibrium. P2 is the more stable product. So again, since it can get over that activation energy hump, it's going to go ahead and probably go to P2 eventually as we move things through. So this one would be thermodynamically controlled. Now some people might go, oh, can it also form P1 at the same time? Yep, it can, but those are going to eventually come back here, and thermodynamically, eventually our sink's going to end up at P2, where all the reaction will dominate at the end. Okay. In between, so if we're not at a very high temperature or at a very low temperature, sort of the ideas that I just talked about, you're going to end up with multiple different equilibria, and some complex situations that happen as a result of that. Okay. Last thing we need to talk about is something we've already presented all the information on this, but we're going to call this coupling reactions, which it's just a fancy way of saying when I combine reactions and I manipulate their thermodynamic or kinetic variables, how do I deal with that mathematically? Okay, so reactions with known values can be coupled to produce a new reaction. So this is like when we're adding reactions together to make a target reaction. When we couple reactions or half reactions, we may multiply by a factor or reverse the reaction before we couple or add them together. We've seen this a bunch of different times, all different applications of Hess's law. All right? So the big thing for us to understand is that when something is kinetically controlled, we're talking about equilibrium constants. When something is when we're talking about thermodynamics of a reaction, we're going to be talking about things like delta G, delta H, delta S. Okay? And how we deal with coupling the reaction equations in these situations is different. Right? As we've done a lot of in this unit, if we multiply a reaction equation by a factor, so take all the coefficients and multiply them by 2, we know that we multiply the free energy, the enthalpy, or the entropy by 2 as well. Okay? If we reverse the reaction, okay, so we flip it around, we know that we're going to change the sign. So if delta G, delta S, or delta H were positive before, we're going to make them negative. If they were negative before, we would make them positive. And then in the end, once we've got everything set up and we add reactions together, we add those values together. Okay, so whatever the delta H, S, delta G values are, we add those after we've manipulated them. Remembering back a unit ago when we deal with equilibrium constants, or K, what we do is if we multiply a reaction by a factor, we raise the equilibrium constant to that factor. So multiplying by 2 would give us a K that is squared. Okay? If we reverse the reaction, okay, so sending the reaction in reverse, then we're going to go 1 over K for that. And last but not least, when we add the reactions together, what we do is we multiply the values. So mathematically, we deal with kinetics and equilibrium constants differently than we deal with thermodynamic values like delta G, delta H, delta S. All right, those were the final things that you need to understand about kinetics and thermodynamics. Go ahead and add summary questions to this set of notes.